Hey guys, so today's lesson is dealing with critical points. We're going to talk about what a critical point is, what it does for us when we're talking about derivatives, and then how that relates to a function's graph. So we already know that there's some relationships when we're talking about a derivative and its function. But now we're going to start focusing on these ideas of critical points to help us identify key features of a graph. Today, really, we're going to focus on how to identify where extrema could occur, and that is dealing with critical points. So first, let's go ahead and take a look at this graph that we have here. And we notice that we have highs and low points here, and we've talked about all different types of non-differentiability. We've talked about corners, cusps, vertical tangents. We talked about discontinuities and all that. So we can see some of that going on here. But my point, my purpose in this is to just be able to identify our extrema, our relative extrema and our absolute extrema. So the first thing we notice here, let me go back here. At this first point up here, we see that that's an open circle. So there's no relative extrema here because the interval that we're talking about, the domain, is an open interval. So we're not talking about that point. So the first point that we have that's an extrema is this point right here. That is a relative minimum or a local minimum, okay? And then at this point we have a local maximum, okay? And then here we have another local minimum because right around it, it is the lowest point within its small window, okay? We have a local minimum there, but it's also the absolute minimum because it's the lowest point on the graph. And then again, we have a relative maximum, a relative minimum right here. And at this end here, we have, this point is higher than all its points immediately around it within its neighborhood. So we say that that's a relative maximum as well. Now, notice there is no absolute maximum because even though this is a high point, this is a high point, this is a high point within their windows, none of those are the highest points. In fact, these points here end up being higher than all the other points. But because this is an open circle, there is no absolute maximum there. Okay? So now as we look at this graph, the question we have to ask ourselves is, if we were to do this analytically, if we were to try and find extrema of a function analytically, what would we be looking for first? Well, where do we see a relative extrema or an absolute extrema occur? Okay, so notice there's no global max, said that already. Okay, where do any types of extrema occur? So what do we notice happening here in regards to calculus, in regards to derivatives, because that's what we've covered so far? What is happening at this point? Well, the derivative at this point is 0. I can draw a tangent line that's horizontal to the graph here. Same thing here at this point. I can say that the derivative at this point is 0 because there's a horizontal tangent here. Same thing here, same thing here, okay? So the first thing we note is that we get these ideas, possible places where extrema occur, is first, one of the candidates we'd say is at places where the derivative is equal to 0. The derivative is equal to 0. The second place that we notice here, and I'm kind of jumping around here, but we notice that we have another relative maximum here at an endpoint. So that's another potential candidate for where extrema can occur, are at endpoints. Now you'll notice on this side, there is no extrema because it's an open circle, but we still want to consider endpoints as candidates because we're just looking for potential extrema here. So when endpoints occur, that is where an extrema can occur, where we have the derivative equal to 0. So when we say the slope of the curve is 0 or f prime equals 0, okay? But then notice, I haven't talked about this one yet. At this point, the derivative is not 0. We would say that the derivative at this point does not exist because we have some sort of corner or cusp here. So that is a third place where extrema could occur. So those are the three places that we need to look for when we're trying to find relative extrema and absolute extrema. The first one is at endpoints, the second one is when the derivative is equal to 0, and the third one is when the derivative does not exist. So we're going to look at all of those in the next few frames and see what ends up happening in a graph. Okay? Now these places that we just identified are called critical points. Critical points are points on the graph where extrema can occur, where they may occur, not where they have to occur. Well, let me rephrase that. They may occur there, or there may be nothing there. There may be no extrema there. But the point is, you're not going to find an absolute maximum, an absolute minimum, a relative max, or relative min any other place than critical points. You just can't. So critical points, again, are those three things. When f prime is equal to 0, when f prime does not exist, right? And that would include any kind of discontinuity, so a jump discontinuity or a removable discontinuity or something along that line, or at endpoints. So critical points are these three things. So if I'm going to ask you what are the critical points, you have to go through the motions and identify when f prime is equal to 0, when f prime does not exist, and identify the endpoints. Now, once you do that, if you have all those points identified, then you can say the extrema for this graph must occur in these points. They cannot occur anywhere else. That doesn't mean those points are extrema. It just means that the extrema must occur within those points if they do exist. Okay? All right, so let's take a look at an example of this. Okay? We want to identify all types of extrema for this function, x to the 5th over 5 minus x to the 4th minus x to the 3rd plus 9x squared plus 9. Okay, so we're looking for all types of extrema, relative and global. So the first step in identifying extrema are identifying critical points. So let me go ahead and write down this function here. We have f of x equals x to the 5th over 5. Let me do this. Instead of x to the 5th over 5, I would rather it be 1/5 x to the 5th minus x to the 4th minus x to the 3rd plus 9x squared plus 9. Now you'll notice that it gave us a domain, it gave us an interval that we're looking at here. We're looking at the closed interval negative 2.5 to the open and 4 here. Okay. So we have three types of critical points that we have to find. So what I'm going to do right now is I'm just going to go ahead and make a list just down here of the critical points. Well, remember, the three critical points are when the derivative is equal to 0, the derivative does not exist, or at endpoints. So if we look, we already have endpoints within this interval. We have endpoints of negative 2.5, and we are still going to consider 4 as a critical point for now, because even though 4 is not part of the function, part of the graph, it's going to give us some information on whether there's an absolute max or whether there's not, or whether there's an absolute min or whether there's not. So I'm going to say the critical points, the first two critical points I care about are when x equals 2.5 and x equals 4, because those are the endpoints. So that's the first type that we're looking for. The second type that we're looking for is when f prime is equal to 0. So I was given the function here. I need to find what f prime is so I can figure out when it's equal to 0. So I'm going to take the derivative of f. Now this derivative should be easy. This is all polynomial, so we're just going to use the power rule here. The derivative of 1/5 x to the 5th is just x to the 4th. The derivative of negative x to the 4th is negative 4x cubed. And then we have negative 3x squared plus 18x, and then plus 0 there. So that's the derivative. Now we need to figure out when the derivative is equal to 0. So we're going to set the derivative equal to 0 here. Okay. Okay. And then we're going to go ahead and try and solve that function there. So we're going to factor out an x. So it's going to be x times x cubed minus 4x squared minus 3x plus 18. Okay, so let me go ahead and skip a step here. Okay, through algebra, through algebra 2 and your pre-calculus class, you've learned how to factor this. Now, you're going to find that in reality, when you talk about factoring in calculus, really like on the AP exam, things like that, you're never going to really have to factor anything more than an x squared function. You may have x to the third, but then you can factor out an x. There'll be a common x factor. So I'm not saying there's no need to know how to factor these. You should already know how to factor them, but I'm not going to stress over that right now because that's something you should already know. So the factors are x, x plus 2, x minus 3, and x minus 3. Okay, so now we need to solve this. Well, we're going to use the zero product property from Algebra 1 here. And the solutions for when the derivative is equal to 0 is when x equals 0, when x equals negative 2, when x equals 3, and then when x equals 3 again there. Oh, I had a little typo here. We have a critical point of negative 2.5, not 2.5. And that's going to affect things because we have critical points here that would have been outside of the interval 2.5 to 4. But in fact, they're all within this interval here. So now we can add to our list of critical points. We have critical points from endpoints. We have critical points for when the derivative is equal to 0. So those are more critical points. And then the third type of critical point is when the derivative does not exist. Now in this case, we're kind of fortunate because this is polynomial. Polynomial is a nice, smooth function. In other words, the derivative exists everywhere. There are no vertical tangents, there are no discontinuities, there are no corners or cusp or anything like that. So in all reality, we've checked all three things. First critical point are in endpoints. Second critical point are when the derivative is equal to 0. And the third one is when the derivative does not exist. So we don't have that issue here. The derivative exists everywhere. So these are our critical points. These are our potential candidates for relative and absolute extrema. So now the next step in this process is to figure out what kind of extrema these produce. Now our goal is to try and do this without graphing it. We want to be able to do this analytically. So I'm gonna real fast just rewrite the critical points here so I have a little bit more room down below. Negative 2.5, 4, 0, negative 2, and 3. Okay. Okay, and then we'll skip down here in the lesson here. This is the work that we just showed here. So our critical points are right there. And on the lesson, I've put them in order, in numerical order from least to greatest. And the reason I do that now is because of the next step. The next step, I'm going to draw a number line. Now, this number line is a great resource in determining what's happening to the function at different places. So we have negative 2.5, negative 2, 0, 3, and 4. Okay, so that's my number line. Now these values down here are x values. Okay, these values down here are x values. And then we got from this that at negative 2, the derivative was 0. At 0, the derivative was 0. And at 3, the derivative was 0. So all these values up here are going to be f prime of x values. Okay? Now, at the ends here, we know, looking at the interval, we know at negative 2.5, this is an endpoint here. And at negative 4, it's an endpoint, but it's an open endpoint. So I'm not going to put anything above that because that doesn't exist. But now what I want to do is I want to go back to remembering the relationship between a derivative and its function. So if you remember, we've gone through this idea of this chart, that when a function is increasing, when the function is going up, the derivative of that function is positive. And when the function is decreasing, when that function is going down, the derivative is negative. Okay? So watch what I'm doing here. If I can identify the domain or the interval for which the function is going up, and then find the intervals for which the function is going down. So where is the function increasing, where is the function decreasing? If I can identify those things, right there, I have a relative maximum. And in the other way, if I can identify when the function is decreasing and then determine when the function is increasing, I have a relative minimum there. So this is kind of cool stuff here. Now, what I know is that on a graph, the graph cannot change directions unless one of the three critical points occurs. You can't have a high point without the derivative equaling 0, the derivative not existing, or at endpoints, which means if we don't have a high point, we can't have a change in direction. So that means these are the only potential candidates where the function could change direction. In other words, all the x values in between there will produce the same sign on f prime. Not the same values, but the same sign. So if one value between negative 2.5 and negative 2 is positive, one derivative is positive, then all the values will be positive. So we only have to really check for one candidate there. Now, I'm going to go ahead and look at the lesson here and identify those same values on the lesson. Okay. Now, what I'm going to do, I kind of jumped ahead there, but I'm going to pick a point between negative 2.5 and negative 2. So like negative 2.1 or negative 2.2 or whatever value you want to pick that's in between them. It can't be either one of those, but in between them. I'm going to take that and I'm going to plug it into my derivative function. So I'm going to plug in negative 2.5 to my derivative function here. So I'm going to find f of negative 2.5, okay, or negative 2.25. Okay? And I'm going to figure out the sign value there. Now, I don't have it here, but if you were to plug in negative 2.25 and get a number out, that value is going to be, right here, is going to be a positive value. You can see that I put a positive sign for that little interval there. So there's a positive, all the derivatives between x equals negative 2.5 and negative 2 are positive values. Now, I'm going to look at the next interval. I'm going to look at the interval from negative 2 to 0. And I'm going to plug in a value in between there. So I'm going to plug in an x value like negative 1. I'm going to plug it into my derivative function. And I'm going to get something out of there. Well, when I plug it in, I'm actually getting a number, and it's going to end up being a negative number. And just off to the side, I'll do that real fast for that one because it's easy. F prime of negative 1 would be negative 1 to the 4th minus 4 times negative 1 cubed minus 3 times negative 1 squared plus 18 times, oh, I'm running out of room here, negative 1. So then this becomes positive 1. This becomes, let's see, negative 1 times negative 4 is positive 4. We have positive 1 there, minus 3. And then we have plus 18 times negative 1, so minus 18. So 1 plus 4 is 5, minus 3 minus 18. That is 2 minus 18, which is negative 16. So it doesn't matter what the value is. What we care about is the sign, because all the derivatives have to have the same sign within that interval. So we know that's a negative derivative there. Okay, now, let's see here. We're going to pick a value. We're going to pick another value between 0 and 3 and do the same thing. So we'll plug in 1 here. If I plug in 1, I got 1 minus 4 minus 3 plus 18. That's going to end up being a positive value. Okay? And then I'm going to pick a number like 3.5 because that's between 3 and 4. So if I plug in 3.5 there, you actually notice that we have a positive value in between there. Gotcha, because I'll bet you were thinking, if that's positive and negative, that's going to be positive, that's going to be negative, it's going to keep going in a pattern. That's not the case. That's not always the case here. And the reason it didn't change here is because essentially we have two factors of x minus 3. But that's beside the point. Now let's interpret what this means on the f graph. So we have f prime, and we have the signs of f prime. Now think back. If the derivative is positive, that implies that the function is increasing. So I'm going to just draw a little arrow, draw a line with an arrow that indicates that the function is increasing in this interval. And then because the derivative is negative, that implies that the function is decreasing. The function, or the derivative is positive, so the function is increasing. And because the derivative is positive, f of x is going to be increasing. So we have a graph that's roughly looking like that now. We get a decent idea that the graph starts somewhere. It goes up, it goes down, it goes up, and then notice at 3 it kind of flattens out because the derivative is 0, but then it goes up again. So we have a function that looks kind of like this, something like this. This isn't perfect, but it's an idea of what's happening. And really, we don't care what that graph looks like specifically because we're trying to solve this analytically here. All right, so now that I know what my critical points are, and I've identified what's happening to the derivative within each of those intervals, I know what the function is doing within each of those intervals, okay? So now what I can say, and this is kind of the cool part, this is the really cool part here. If the derivative was positive and it changes to negative, that implies at x equals -2 that we have a relative maximum at x equals -2. We can see it here. It went up, and the f function went up and then went down. And then at 0, the function was going down, and now it's going up. Therefore, we have a relative minimum here. Okay. Then at 3, we notice the function was going up, f was going up, and it continued going up. So there is no extrema there. And that's what we're talking about with critical points. Critical points are only candidates. Critical points are not necessarily extrema or going to be where extrema occur. They're just potential candidates for that. Now, here at 4, if you remember, at 4, this was an open interval, so we're not going to have an extrema at 4 here. But at -2.5, we do, because this is a closed interval over here. So notice, if you look at this, we are starting at x equals -2.5, whatever that height is, whatever that height produces, and the function is increasing from it. It's going up from it, which means this point is a relative minimum within its small window. Okay? So there we've identified all our relative extrema, or at least where they occur, the x values for which they occur. So there's a relative minimum at x equals -2.5, a relative maximum at x equals -2, a relative minimum at x equals 0. Nothing's going on at 3, and nothing's really going on at 4. So those are where our relative minimums and maximums occur. Now it says identify all types of extrema for that function. So I'm going to want to figure out what the absolute extrema are. Now, the absolute extrema, remember I said a little bit ago, that absolute extrema first have to be relative extrema. You can't have an absolute maximum unless it was first a relative maximum, if that makes sense. You can't have an absolute minimum unless it's first a relative minimum. So one of these is, well, I can't even say that. These are now candidates for absolute minimums, and this is now a candidate for absolute maximums. And here's why I say they're candidates and not necessarily the actual values. Because the graph could be looking like this. We don't know yet. It could be going up, then flattening out, and then going down, and then flattening out, and then going up, and then flattening out, and then going up again. Now remember, this was a closed interval, and this was an open interval. So if we look at this, we can see in this graph, that doesn't necessarily reflect this, but it's just the trends, that here we have an absolute minimum, but here, this was our only relative maximum when x equals -2. This was our only relative maximum, but it's not the absolute maximum because we have values that are above it. In fact, there would be no absolute maximum in this graph that I drew here. So just because it's the only relative maximum does not mean it's automatically the absolute maximum. So the way we go about figuring out whether it has an absolute max or an absolute min is to take all our critical points now and actually evaluate what the value of the function is there and to see what those values actually are. So I'm going to spare the time here, and I'm just going to go through and plug in -2.5 to the function f to see how high the function actually is or how low the function actually is at x equals -2.5. So you'll see that when x equals -2.5, f is 22.281. And then I'll plug in the next critical point, -2, and I get f of -2 equals 30.6. If I plug in x equals 0, I get f of 0 is 9 right here. Now notice I'm not plugging it into the derivative function. I'm not plugging it into this guy. I'm plugging it in to f of x, because I want to know the values of the function now, not what the derivatives are. So I'm going to plug in f of 3. Well, I don't even need to plug in f of 3. I'm not going to plug in f of 3 because f of 3 is not a relative max or minimum. We've already determined that because essentially the derivative sign did not change. I am going to plug in f of 4 because I need to see whether that is higher or would be higher than all the other points. So what I notice here is that between the relative minimums, okay, we have a relative minimum of 22.281 and another relative minimum of 9. So that would imply that the lowest value is actually 9. So f of 0 is our absolute minimum. Now when we're talking about absolute maximum, well, our relative maximum was 30.6 right here, right? Relative maximum when x equals -2 is 30.6, but f of 4 was 37.8. So this value is greater than this value. Well, you might say, who cares? That's not part of the function. You're right in one aspect, but the function had to go up. So f of -2 was 30.6. So -2 here was 30.6. And then if f of 4 existed, it was 37.8. 37.8. So this point is higher than this point, and this point doesn't exist, so who cares? But the function had to increase to get to this point, so that means there was points right underneath it that were higher than this point. So we would conclude then that the relative minimums are y equals 9 and y equals 22.281. The relative maximums are y equals 30.6, and then our absolute minimum is y equals 9, and we don't have an absolute maximum. There isn't one. It does not exist. Okay, so there's a good example of finding critical points and doing an entire problem to find relative minimum, relative maximum, and all types of extrema. So let's go ahead and take a look at another example here. It's a little bit different, but it shouldn't take nearly as long. So let's go ahead and look at this function. So it says identify all types of extrema for the function. So we have f of x equals -x minus 2 raised to the 2/3 over the interval -1 to 4. And we're looking for all extrema. Well, the point of today's lesson is critical points. And what are critical points? Critical points are candidates for when extrema occur. We cannot find extrema unless we first find critical points. So again, there's 3 types of critical points. The first ones are at endpoints. The second ones are when the derivative is equal to 0. And the third ones are when the derivative does not exist. So the first critical points we notice here are at endpoints. Well, we have a closed interval all the way around. So that makes it nice. We have critical points of -1 and 4 because those are endpoints. Now we need to look for the other critical points. The next critical points are when the derivative is equal to 0 or when the derivative does not exist. So in either one of those cases, we have to find the derivative here. So we're going to take f prime of x. When I take the derivative of this, this is another chain rule and power rule combined. So the outer function here is negative something to the 2/3 power. So the derivative of that's going to end up being -2/3 times x minus 2 raised to the -1/3 power, because we have to subtract 1 from that. And then times the derivative of the inside. Well, the inside was x minus 2. So the derivative of x minus 2 is just 1. So in all reality, we don't even have to represent that there. So that's the derivative. Now before I go any further, I see a negative exponent here. So I'm going to go ahead and rewrite this so that's a little bit easier to see analytically here. So -2/3 times x minus 2 to the 1/3 instead of Having a negative exponent, we'll move it down and make it a positive exponent. That'll make us able to see things a little bit easier now. Now, we want to identify when f prime is equal to 0. Well, if we have a fraction here, f prime can only equal 0 if the numerator is equal to 0. And in this case, the numerator can't equal 0 because it's a constant, it's -2. So f prime does not equal 0 ever. But f prime does not exist at a very certain point. Remember, there's two things in math that we're not allowed to do. We're not allowed to divide by 0, and we're not allowed to take the square root of a negative number in the real number system. Okay? So we would say that f prime of x does not exist when x equals 2. Because if x equaled 2, we'd be dividing by 0 there. So that's another critical point that we have. Critical point of -1, 4, and 2. And again, f prime can never equal 0. Therefore, these are my only critical points. It's a lot easier than the last problem, at least in that regard. There's only 3 critical points here. So from here, we're going to take those 3 critical points and we're going to draw a number line and identify what's happening at each of those critical points. Okay? So remember that the -1, the 2, and the 4 are x values. So I'm going to put an x down here to remember that. And the top numbers that I put down are going to be the f prime values. Well, at x equals 2, f prime did not exist. So I'm going to put a DNE here. And when x equals -1, that was an endpoint. And when x equals 4, that was also an endpoint. So now these are the only places where I can get extrema, which means these are the only places that the function could possibly change directions, which means that the function cannot change direction between x equals -1 and x equals 2. So whatever direction the function is going in this interval at any point, it's the same direction throughout that entire interval. So again, remembering that the sign of f prime determines the direction of the function. If f prime is positive, then f is increasing. So we're going to pick a number between -1 and 2. Well, a nice easy one to pick is 0. I like 0. If I plug in 0 to x, to f prime here, so I'll do this off to the side so we can see it. We're going to say that f prime of 0 is -2 over 3 times 0 minus 2 to the 1/3. Okay? Now, I don't really care what that exact answer is. The only thing I care about is the sign. So in this case, the top number is a negative number. Okay? The bottom number, 0 minus 2, is negative. Well, raised to the 1/3, remember, raising to the 1/3 means the cube root. So the cube root of a negative number is a negative number, and then a negative times a positive is a negative. So f prime of 0 is actually going to be a positive number because a negative divided by a negative is a positive. So if f prime of 0 is positive, that means within this interval, f prime must be positive everywhere. Okay? Now we're going to pick another point between 2 and 4. So a point between 2 and 4 is 3. So we'll plug in f prime of 3. F prime of 3 is going to be -2 over 3 times 3 minus 2 to the 1/3. So that's going to be negative on top. 3 minus 2 is 1. The cube root of 1 is 1 times 3 is positive 3. So that's going to be a positive. And then a negative divided by a positive is a negative. So the derivative at 3 is negative. That means the derivative between the interval of 2 to 4 is also negative. Okay? So that gives me a lot of information about what's happening on our graph. Okay? I think I need to get some new markers here. I'm not staying on or getting rid of the board very easily. All right. So now, since the derivative is positive, that implies that f is increasing. Since the derivative is negative, that implies f is decreasing. So looking at this, now we have an understanding for what's happening on the function. We know that at x equals 2, we have a relative maximum because the function is increasing on the left-hand side and decreasing on the right-hand side. Therefore, it's a relative maximum. So when x equals 2, there is a relative maximum. When x equals -1, we're at a point here, and the function is increasing from it, which means this point is lower than all the other points around it. So this is going to be a relative minimum. And then at x equals 4, here's x equals 4, the function is decreasing to it. So we have a function that's going down and hitting the endpoint here. That implies that f of 4 is actually going to be a relative minimum again, okay? So here's essentially what this graph looks like. We have a does not exist at 2, okay? The function itself is continuous at 2, but the derivative does not exist at 2. That would imply that we're either going to have a vertical tangent or we're going to have a cusp. Well, because on the left-hand side we're increasing and on the right-hand side we're decreasing, we're going to end up with a function that looks like this. It's going to end up being a cusp, something like this. And now we can see at -1 we have a relative minimum, at 2 we have a relative maximum, and at 4 we have a relative minimum, okay, at x equals 4. Okay. Now the next step is to figure out what those actually are. So let me get this up here. We've identified the critical points, we've determined the signs of f prime in those intervals, and as a result we know the direction of f, and then as a result of that we can say that this is a relative maximum or a local maximum. We can say that these are each local minimums. And then out of those three critical points, we're looking for our absolute extrema. So we're going to take these values now and plug them back into f of x and see what we get out of it. So if I plug in -1 here, if I plug in -1, f of -1 ends up being -2.080. F of 2 ends up being 0. If I plug in 2, you can see it. 2 minus 2 is 0, raised to 2/3 power is 0. F of 4, if I plug in 4 there, I end up getting -1.587. Okay? So those are the three y values of our extrema. We can see that f of 2 was actually our relative maximum. It is also our global maximum. Okay? And then between our two relative minimums, the lowest one was when x equals -1. So our absolute minimum is -2.080. Okay? So you can take a look at that there. Okay. Now later on in future lessons we're going to go more in depth on justifying why we have a relative maximum. We can see it in a picture, but this is not considered valid justification on an AP exam. It's not considered valid justification in my class. It's a good help. It's a good way for us to visualize what's happening. But we're going to talk about more of how to justify these things in words so that we can express ourselves logically, okay, later on in future lessons. All right. So here is a last slide with two examples on it, or two practice problems that would be great to look over and get an idea of the extrema. So first thing you have to do is find the critical points, and then from there determine if those critical points give you a relative max, a relative minimum, or neither. So go ahead and give these a shot. Okay, so for number 1, we have y equals 1 over x squared minus 1. That's our function. And we're looking for any extreme values of that function. So we've got to find all the three critical points. So the first type is when the derivative is equal to 0. So I have to take the derivative. Now to take this derivative, you could look at it one of two ways. You can use the quotient rule, There's nothing wrong with the quotient rule. In fact, I'll do it real fast. The quotient rule says the derivative of the top, which is 0, times the bottom, minus the derivative of the bottom, which is 2x, times the top, all over the bottom squared. Okay, we could do that. And then that simplifies, that all cancels out, to negative 2x over x squared minus 1 squared. Okay, so that's the derivative. I would personally like, I don't know why I like this, but I personally like rewriting a function like that so that it looks like this. Y equals x squared minus 1 to the negative first power, and then I would use the chain rule on that. You'd end up with y prime equals negative x squared minus 1 to the negative second times 2x. And then you could rewrite it like this. Now ultimately this is going to help us solve this problem a lot faster than this will, so we're just going to go with the quotient rule. All right, from here we're going to set the derivative equal to 0. Set the derivative equal to 0. And solve this. Now when I go to solve this, the best way to look at this is to cross multiply. So when I cross multiply, 0 times x squared minus 1 squared is 0, and that's equal to negative 2x. We'll divide by negative 2, so x equals 0. So our first critical point is when x equals 0. Now, from there, we also have to figure out when the derivative does not exist. Well, the derivative does not exist in two places, either when you're dividing by 0 or you're taking the square root of a negative number. So we would be dividing by 0 on the derivative if the denominator was 0. So we would say y prime does not exist when x squared minus 1 squared equals 0. Okay? Now we can go through some really long process in solving this, but I see a square on the outside, so I'm going to square root both sides and simplify it to say x squared minus 1 equals the square root of 0, which is 0. I'm going to factor this, so I get x plus 1 times x minus 1 equals 0. And then as a result, we get x equals negative 1 and 1. So the derivative does not exist at those 2 points. So those are another 2 critical points in our function. Now, if you notice, there was no domain restriction, so we have no endpoints to this function. So these are our only critical points here. But our number line is going to look a little different as a result of it. When I set up the number line, I don't have an endpoint. This is going to just keep going. So we've got negative 1, 0, and 1. Now, we're going to go through and again identify what these are. When x equals negative 1, the derivative did not exist. When x equals 0, the derivative was 0, and when x equals 1, the derivative did not exist. Okay? So this is our y prime line, and this is our x line. We're going to pick numbers in these intervals. Now we have to include numbers that are within the interval negative infinity to negative 1, and then also from 1 to infinity. So we're going to pick like a negative 2 there. If I plug in negative 2 to my y prime, if I plug in negative 2, the top is going to be positive, the bottom is going to be positive, so I'm going to end up with a positive value on top, or in that interval. If I plug in like negative 0.5, again, this is going to end up being positive, because negative 2 times negative 0.5, that's positive. If I plug in a negative 0.5 here, it doesn't matter what's going on there, I'm squaring it, so the bottom is going to be positive. So again, I got a positive divided by a positive, which is a positive. And then if I plug in 0.5, the top's going to be negative, the bottom's going to be positive, so then when I divide that, I get a negative. When I plug in like a 2, I get a negative on top and a positive on the bottom, so again, a negative. Let me do this real fast. Rewrite our critical points a little higher so we can do something with this. So again, our critical points were x equals 0, negative 1, and 1. Now, I always like putting these arrows in. This y prime being positive means that the function is increasing, the function's increasing, the function's decreasing, the function's decreasing. So really what we have here is, if I were to factor this, you would see that we have vertical asymptotes. We have infinite discontinuities here because, just as a side, I can rewrite this as 1 over x plus 1 times x minus 1. So that is why the derivative did not exist at those 2 points, because you had vertical asymptotes. But what do we notice here? We have the function increasing, then it's increasing, and then it's decreasing and decreasing. So there is no relative extrema here because the derivative didn't change signs. There is one here. This is going to be a relative maximum. And then there isn't one there. So, so that's it. Our relative maximum occurs when x equals 0. So we can plug that back in to find that value out. But the bottom line is we have a local maximum when x equals 0. We take that, we plug it back in up here. We get a y value of -1 when we plug in 0. So our local maximum is 0, -1 for that problem. For the last problem, we have y equals x cubed minus 3x squared plus 3x minus 2. Okay, so we're looking for extrema again. We're looking for critical points, so we have to take the derivative. The derivative would be 3x squared minus 6x plus 3. We're looking for when the derivative is equal to 0. So we're going to set that equal to 0 now. I'm going to factor out a 3 here. Okay, and then I'm going to do some quadratic factoring. So that's going to be x minus 1, actually x minus 1 squared, but I'll write it as x minus 1 times x minus 1. So that is the factored form, which means x equals 1. So now we have a critical point of x equals 1. Our next set of critical points are when the derivative does not exist. This is polynomial. The derivative always exists. And then endpoints. There are no endpoints. So we only have one critical point here. That's nice. Well, if I look at this one critical point at x equals 1, we know that the derivative is 0. The derivative is 0 at x equals 1. So y prime is 0 when x equals 1. Now we're going to pick some points that are to the left of 1 and to the right of 1. So to the left of 1 is 0. If I plug in 0 to y prime, I end up with 0 here, 0 here, so it's a 3. So this side ends up being positive. If I plug in like 2 here, if I plug in 2, I'm going to end up with, let me do the work here. Y prime of 2 is equal to 3 times 2 squared minus 6 times 2 plus 3. So that's going to end up being 12 minus 12 plus 3, which ends up being 3. So y prime of 2 ends up being positive again. Okay? So what does that tell us about the graph? What is happening with this graph at x equals 1? Well, we know that if y prime is positive, that y is increasing. Y prime is positive again, so y is increasing. There are no other critical points. This point, there is no extrema because the derivative didn't change signs, which means the function did not change direction. So in this case, there is a critical point at x equals 1, but there is no extrema. There's no extrema. And the reason that's the case, if you look at this, if you were to graph this, it's going to look something like this. When x equals 1, that value of 1, wherever that is, whatever that value is, the function's increasing, and then it's flattening out there, and then it's increasing again. And some of our x cubed functions, our parent x cubed functions, look like that. Some x cubed functions look like this, and so we would get extrema. But in this case, we don't have that because the derivative did not change signs. Again, the function did not change directions. So that is the end of this lesson. So go ahead and get some more practice on your own, and then I'll see you again tomorrow.